Good morning. It still is morning, so we can say that. In TGIF, we have a habit on Fridays around here of trying to host something of interest to get our brain cells going, because by Friday they're all dead, right? So today we're going to do that. We're just delighted to have Tom Cwik with us here today. And I want to give you a little bit of a background. He's a Chicago guy, born and raised, maybe not born, but at least raised in Chicago, came here to the U of I for all 3 degrees. So he has degrees in electrical engineering, bachelor's, master's, PhD. And his time here in the recent past, more than just recent, has been at NASA JPL, the Jet Propulsion Lab in Southern California. And his time there has ranged from being a technical supervisor to a proposal manager to a principal member of the lab. It includes time where he was manager of the HPC group there at JPL. And he's now the manager of the Space Technology Program Office. He has successfully blended engineering, technology, things like robotics. I'm proud of the fact that he can spell double E in HPC. He lives on the edge where few people live, and he's leading a team that tries to do things that nobody has ever done. Please welcome Tom Cwik.
Thank you very much. Thank you, Merle. It was a real pleasure to come back, and especially here at NCSA, where it all started. You know, obviously, in high performance computing and computing, the current generation, being out, what it was at the edge, what is now, the reality of computing. It all started here, and so to be back here and to be able to talk is it's a real honor and pleasure for me. Coming back also, being out on the West Coast, you hear about, the 3-letter schools, technology schools on the West Coast and the East Coast. And then you come back, here to the heartland, and you realize I'm always reminded, not that I really should be or have to be, but I am always reminded about the excellence, broad excellence here in the community at the U of I. It's recognized, so it's always great to come here and get reinvigorated back at Illinois. What I'd like to talk about today, this will be a sort of a little fun talk. It's going to be a mixture of some results, pretty pictures, some of the graphics, the images we have coming down from our spacecraft and satellites, remote sensing, blended together with what I see as some of the problems, issues, and challenges and goals, and what we could do with advanced computing in the space business, in space exploration. I'll try to talk a little bit about, what are the challenges, where we're at today, and then what are the challenges. The challenges come technical and cultural, as we kind of know in the high-end computing world. There's a lot of cultural change that has to happen along. It's just natural. It's part of the deal, I would claim. And the technical issues, and then where we want to be. And so I'll show a video and kind of remind us of our Mars landing, because that was exciting, and then walk through. A little bit of context. Here's a selfie of Curiosity that was completed last month. 2+ years now it's been on the surface. It landed, it roved various directions to where now Mount Sharp over to the left, sort of a 3,000 meter peak, where it's going to exposing, the whole point was that it exposes the stratigraphy, the layers. And so if you got your geology background hat on, if you got layers, you're starting to look at history and what's coming out of those layers. And so that was the whole point of this mission, the science of the stratigraphy, and then leading to life on Mars, understanding life on Mars. That rover there is about 900 and just under 1,000 kilograms, 960 kilograms, about 2,000 pounds. It's about as big as a Mini Cooper. And what you live with here is that the power source on that in the back is our RTG, radiothermal isotope generator, a little bit of plutonium, actually very small, a bit, produces heat heat is transduced into electricity. So when it landed, beginning of life was 110 watts. So the rover has to work off of 110 watts continuous. You got batteries, you charge them up, you deplete them in a power cycle. You're sitting on the Mars atmosphere of about 1% of Earth. You are living in a thermal environment where actually it gets above freezing. In fact, it can be in the summertime near the equatorial regions and where the rover is, where Curiosity is, quite a bit warmer than today, and in the 30s, and then drops immediately overnight, no atmosphere, down to minus 100 degrees Fahrenheit. So you have to live with that thermal environment and everything that brings you. It's about 37% of the gravity of Earth, and so you got this gravitational difference that you got to worry about when you're designing. So maybe you've seen this video. If not, if you did, it's a reminder. Otherwise, it'll show you, kind of in a fun way how the landing went.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0, in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land, and we head straight down to the bottom of a crater right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the Skycram maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
So those are some of the key folks that engineered the system at JPL. Now they're engaged in the next generation. I'll talk a little bit about where we're going with that. Here's, when we landed, here's looking down. That's the heat shield from the top. So the heat shield ejected that lens cap, and it fell away. And now you're at the rover, on the bottom of the rover, looking down at it. And then when you got close to the bottom, now you're seeing the engine exhaust, the jet propulsive engines here kicking off the dust on the ground before landing. So let me talk a little bit about, a lot of engineering design, obviously, a lot of testing, and there was a huge simulation. Maybe you've seen some of this in the past. The simulation that so this is obviously 5 years old or so, 3 years old, when all the simulations were being done. They actually were done right up to about a day and a half before it entered the atmosphere. Curiosity entered the atmosphere because it brought back the latest trajectory. You have to hit an XYZ point of that atmosphere, and so you brought back the latest orbital determination of where you are. And then the best understanding of the atmosphere at that time, like any atmosphere, even though it's light, it's moving around in pressure and time. So you brought that back into the simulations, and then you ran then basically Monte Carlos. They're not in terms of, had a very nice tour yesterday of obviously blue waters in the system. There, you're running today Monte Carlo simulations, where the simulations themselves, there's a whole string of them, because you're going from the top of the atmosphere. You're modeling the different bodies, the dynamics of them. You're modeling that parachute. You're modeling the atmosphere. You're modeling the radar system, the radar return, and it's all in a loop where some of the hardware in the loop, some of the software in the loop model is all brought together, and you have a complete set of simulations. The ones that we use are called POST here. This optimized simulate trajectory, and then descends, sort of two different variants of it, two different centers work on this, large groups of people. The key point to all this, why these simulations are done, where you're at, is you're bringing in all the best information you have of the Mars atmosphere and the system you built, and the latest data at that point in the trajectory. But then you have all these unknowns. And so one of the key things we have to work at a lot, of course, is all the dispersion, the input dispersion, the input uncertainty in a large range of variables, which then today, the simplest way to do this, the way that the engineering team can get it to this point in time, is to run the simulations, Monte Carlo simulations. And the whole point is that you want to create this, what's called this error ellipse, the landing ellipse, about 19 by 6 kilometers, through all those dispersions, all the best knowledge of our system. We believe in this case here, 99th percentile, that it's all going to land within that error ellipse there. And that error ellipse then is key, because obviously if there's some hazards in there, if there's some rocks, if there's some outcroppings, if that error ellipse is sitting over here on this steep incline, you have a big problem. And so that error ellipse has to be brought down to an understanding to where to the highest percent of understanding, you're going to land somewhere within it. And obviously, we landed very close to the center, about a couple kilometers from the pick point, from the scientifically designed pick point, a couple years ahead of time. The accuracy of it, there's a whole range post-landing. There's a whole range of the accuracy of all those simulations, and so continuously increasing the accuracy of the simulations. Here's one that I really like. It's very simple. Is we have the Mars Reconnaissance Orbiter with a high-rise camera. It's got sort of on the surface about order meter resolution on the surface, and so some clever guys said we'd like to get a picture from orbit of it landing. Of the Curiosity landing. That's a 22-meter parachute right there. And so the picture on the left is a simulation of if we bring our reconnaissance orbiter to the right place at the right time when it's landing, and we look with our field of view, which was pretty broad. It was broader, much broader than this, but it's only the field of view of a camera from orbit at the right time. We believe we could get that image there on the left at the right time if we snap enough pictures. And sure enough, we capture what I believe is an iconic image here in space exploration, a true picture of the landing from Mars orbit. So that's the accuracy you're at. So where do we want to go with this? What are the sort of the next generation? We're going to land back on Mars in 2020. It's going to be more or less the same system we have today. And now we have a lot of work going on because we would like to go to Europa. So the next generation, I'll talk about this later, for looking for life in the universe, in our solar system, that we could get to, will be on Galileo's moon, Saturn's moon of Europa. It's going to be a different sort of landing. There's no atmosphere, sort of 13% of gravity. It's an icy surface. We'll talk about it more later and at the last part of the presentation. But we have to come to the surface, and not only do we have to do what we did in that first piece, we want to bring in this terrain relative navigation. Because the surface is going to be so difficult to land on, you're going to have to do some things right down to the last meter to land. You don't have a big 20-kilometer flat parking lot to land on. And if we're going to land there, we want to get to exactly where the science is by some definition. There's a lot of understanding of sulfites and whatnot on the surface, and we want to land exactly where they are, because we're probably not going to have we're not going to sit there for years for various reasons. We're going to have a short time frame on the surface if we get there, and we won't have the benefit of being able to drive for a couple of years. So we want to get, so we're calling that science in a loop navigation. As we get to the end, we want to be running hyperspectral imagers, some other type of imagers in real time, in a few minutes time. There's no joysticking from the Earth to get us to where we want to land. One of the things that we hope is going to make that happen is we are finally going to get, again, cross our fingers, a multi-core advanced space computer. Today it's embarrassing to stand here and say that we as a country fly something which is 10, 15 years old in terms of performance for space. We have this issue in space that you have all radiation and temperature and so forth, and you don't have power. And so we've been working very hard now, and we believe we have a path forward to piggyback off some DARPA projects in the past. Telera processor, a multi-core processor, perhaps 49-core processor, operating now in this measurement 24 giga operations. With the important part, it's at 7 watts. The entire system will operate off of 7 watts. And then more importantly, it's being put together in terms of having the power management. You're able to throttle many of those cores up, turn many of them down so that you're not always working off of 7 watts. Maybe you're going to bring that thing down to a watt or a half a watt when it's not being used. That's the future for space computing that we want to be at. And part of all this too, so this is where we want to be. The other part that I really believe is going to be essential in our systems here, uncertainty quantification. Everything we work with, generally in the engineered systems, and very specifically, obviously, in the things that we work on in space, is that there's a lot of uncertainty. And that uncertainty is not something you could fix later. And like, oh my gosh, we built it, tested it, and it wasn't just right, so we'll go back and retest it. It's not the way the space business works. And so we're trying to spend a lot of time here pushing at a small level uncertainty quantification. Can we now start running, examining the engineered systems, examining models, and high performance computing is going to be essential to do this for high fidelity modeling and then more importantly, the integrated model, which then allowed sensitivity of the uncertainties, true uncertainties. If your coefficient of thermal expansion is between 3 and 5, it's not 4. You put 4 in there, you get a number. 3 to 5, you have a sensitivity to that. Can you actually start running one of those complete simulations with the uncertainty built in, with more fidelity in the physics-based model, and then do that early in your life cycle of building the systems, so that you're testing components and then subsystems against the models you're building up over time, better understanding, making better decisions, getting better performance on your engineered systems, and getting better assessment of the risk as you move forward over time. Of course, not everybody likes this. Here's an image that, no, not really. A lot of fun out there, in this, when you go to Mars, there's a lot of interest in the community on these sorts of things. And then, another one of my favorite pictures, they're kind of shown on big screens around the laboratory, and you just kind of walk around, you get to see them here and there. Here's a picture again where you're looking at the two blue, spots there. Those are the both sides of the propulsion engine coming down, burning up the soil a little bit on the surface. It landed, and then you see the first set of rover tracks from where it landed, and then rolling out in the surface here. Again, this is from the high-rise camera in orbit. Another just, if nothing else, a really pretty picture, but of course there's a lot of science going on in there. You got a scoop. The whole point is you're digging up here, went to a sandy soil, digging it up. It gets rolled off into a set of science, a set of instruments, where it's broken down. Different spectroscopy is key in this mission, different sets of spectroscopy, so you're actually looking at, what's in that soil, the water, the perchlorates and so forth that then lead to all the science discussion and understanding. Where it's going, again, this is, looking out at Mount Sharp, where we're heading, and can't see it really in there, but there's a little boulder there. That's where we'd like to go. So you'd like to drive up. You could in your imagination pick a trail that you're going to drive up there to get into all this layering and go behind some of those cliffs. That's, when you sit there, you go, that's where we want to be with this rover. So that's sort of the first piece, the Mars mission, obviously, a lot of, scientifically driven engineering design there. And, where it stands, where we'd like to go with that. Thinking about, another thing, very close, obviously, to the NCSA here, remote sensing data science. Another big piece of JPL is you build the instruments. And once you get into space, the Earth-based remote sensing, as we know, obviously is essential, and then planetary remote sensing with the same sets of instruments, though with many more constraints on them. Something I worked on, the Aquarius mission, sea surface salinity. The ocean is a pretty well-defined physical system, mathematical, physics-based system. You get huge oceanographic models that run, even many here over the years at Illinois, and salinity is one of the key state variables, temperature, pressure, and so on. And salinity drives the entire circulation of our ocean, and understanding that from space was a key measurement. And so a system was built, a space system, launched a couple years ago, now taking every 6-day repeat cycle, 7-day repeat cycle there, looking at basically a little less than 100 kilometer spots on the ocean at any one point, and then making maps of and retrieving the salinity, and then making maps of very, very sensitive measurement. You're measuring noise of the ocean, basically, and you're saying this much noise or that much noise, you could relate it back to the amount of salt in the ocean, a very, very sensitive measurement. And so what you create then are these maps. And you create them, on a weekly scale, and then time scale, and then on a monthly scale, and then on a seasonal, yearly, and obviously then you look over time and for climate. And so the maps then, you can see very interesting coming off what I learned as a non-scientist, you learn that it's fun to talk to the folks in this field. The Mediterranean, a lot of salts wash into the Mediterranean. They get kicked out into the Atlantic there, the mid-Atlantic, and then that actually drives, all that red there and yellow actually drives the Halley's cycle, which moves the conveyor, so-called conveyor belt of the ocean currents, up to the north. It drives all that. And you watch this over time. As you go to the websites, you can see the videos of the breathing Earth. So that's the sort of the measurement. So how do we do that today? So here's where we're at with it. You have the spacecraft. You have a set of data streams, and they come down. And basically today, the way it's done is it goes into big archives, and the archives are separated from then the people that operate on the data. In the NASA archive system, they go off to the different centers and have things called DACs, which hold all the data. And some of it's raw data, some of it's got more metadata. And over the years, this has been a 20-year, 30-year sort of life cycle that NASA's been flying these remote sensing missions. So there's been a path set up the way to do it. That path is not going to lead to, what Dan Crichton, a colleague at JPL, says agile science. What is the next generation here? How do you do this, and how do you evolve into the next generation? So if you look at it, Dan put this together here of, if you want to go to agile science, I think, NCSA thinks about this problem a lot, the LSST and so forth, big data, and what that means. There's going to be a lot of challenges today. We want to get to the point where we have too much data, where we honestly have, gigapixel cameras sitting on that rover, and we have optical comm, laser communications back to Earth, and we're getting basically high-def video rates back to Earth. That is conceivable. We're on a path to be there in 10 years to do that. We should be able to do that. The technical part we could handle with some work. And so we're going to have the challenge, like everybody does, of big data, even from the planets, and incredibly, without a doubt, obviously, from Earth orbit, where we're right on top of it. And then we have the data volumes, the data collection, and what all that means, and then moving into, the data analytics, where you have a science community, many different types of science communities broadly distributed. It's a classic, this problem is getting to be well defined, I would claim today. But it's not getting to be well solved yet today. But I have a sense a lot of it's going to come out of NCSA in the future. And so, busy picture here. One of my friend Dan's pictures, who thinks broadly about these things. And the way I look at it is, you look in that central part about data science infrastructure, data, algorithms, machines. What does that mean to put it together so that you could take existing DACs, data centers, like all that existing data, which is going to increase, and evolve it into the future, so that researchers, application folks, applications to us means sort of like the government who's understanding climate. What does the data tell us about climate? Remove yourself from the politics of climate change, but just go think about the data for climate decision support. Application support, where you want real-time data, earthquake, when you see earthquakes happen in real time, when you see the tsunamis, when you see the fires, that this data is feeding back to them, because we have a lot of resources on orbit. And so, how is this infrastructure going to be put in place to make that happen over time, and what are some of the issues? Another colleague, Chris Mattman, maybe from JPL, big data person. Here's some of what I would call some of his challenges in this area. The big data, how it comes down. To me, this is a technical question, and we're all really good at solving the technical question. We're going to figure this out, right? Give me more data. I'll tell you, you want, optical communications, you want bigger fibers, you want T-something lines, and that's going to, but it's a problem we got to really work on. Then you have the cultural problem, and as we all know, right? I will not change. I got my MATLAB. I know how it works, right? The data comes in. I have to understand how this works to put, responsible result information out from raw data. And okay, so how are you going to evolve that into the future? And he's working with a snow hydrology project that we're understanding how snow levels are changing. For example, in the Sierra, they're changing greatly over time now. I didn't go skiing last month because there wasn't enough snow in Mammoth. That's this year. And then also, some of the other ones. And the other one, I think the third one is a huge problem here, is that the climate models are coming along. I think they have a long way to go. They could get much better in terms of a model that's predictive, and it's going to have to match up against all this data. That's going to become a big problem to put those two together so that the assessments of the models are starting to converge. I don't know if you ever looked at numerical weather prediction. I mean, those models over the years, based on a lot of assimilation of data, those models have very hard metrics on how they're getting better. It used to be a 3-day weather prediction was kind of sketchy. Now it's over time it turned into a 5-day weather prediction is pretty reasonable in lots of parts of the country. And now if you want to start thinking about how to do that with climate. And then same thing, we have a lot of catalog data from the planets. There's actually something called a planetary data system that has that. How do you evolve that into the system? Big data problems. So we could step back here, a little cleansing, just because pretty pictures. This is a true color image, of Cassini, from Cassini, with their, best telescope, looking at Saturn. Cassini now just celebrated recently the 10th anniversary of this system, going strong, extended mission. The consumables, you manage the consumables, the amount of fuel for orbitary change and so forth. Things break or become a little uncertain over time in the space environment. But a beautiful picture looking down from obviously the sun to your left, looking at the rings and the globe of Saturn. Here's one of mine that was sitting on the big screen recently that I walked by, and you're looking at the North Pole of Saturn, and all that structure in the atmosphere of Saturn and the revolution, and as it evolves, the storms, the great red spot, all the coloring, and then looking through the rings. And then again, this is enhanced color, this one here, but just a mind-boggling picture of the rings of Saturn. Again, just an image, spacecraft up there, a camera taking a picture of the rings of Saturn. And then where you'd like to go in the future, we're really going to try to get to Jupiter. Saturn's another distance out there. Here's Enceladus, this icy moon, and best knowledge, we have a true scientific belief today, understanding today, that there's a water ocean underneath the icy core. That icy core gets broken by tidal forces, by heat, by exchange, and it's kicking out water, H2O water, the same water that you drink right here, with salts, with a lot of different salts in it, kicking out water through water volcanoes, water geysers, water spouts coming off the surface of Enceladus. And then another, just a fun picture again from Cassini looking back, looked at, said, where's Earth? There's Earth, a little blue dot, but now from the distance of Saturn, 900 million miles away. Okay, last portion of my presentation, where we want to go into the future, that's going to have to be driven. There's going to be predictive understanding that has to come from modeling. There's no two ways about it. If we want to go out to Europa, and this is an artist image, we're not this good yet to take a look at out at Europa, but there's that if you were standing on Europa, this is the best understanding, best guess of the view that you would see looking back at Jupiter with its bands, and this is probably what the surface of Europa looks like. And if you stood there, that's you're on the moon looking back at the planet. And so here, this is a real picture. Most of these pictures, Galileo was a spacecraft of the 90s, launched in 89, if I remember correctly, 89. And through the 90s, it went to Jupiter, and then it went around Jupiter, and then it made special orbits to the Galilean moons, including Europa, and our understanding of Europa in 1996 just changed radically. What we knew about the planets pre-1996 to when all these data came back and the science community got at it, just changed the threshold change in time overnight. What you're looking at here now is Europa. It's about a little smaller than our moon. It's about 13% the gravity of Earth, and it's another icy moon out there. Ice core, down to water ocean, down to a rock central core, ice surface, maybe about 10 kilometers thick. What you're seeing, the red spots there are probably, if you go look at glaciers, you got subduction zones, you got things moving around. You're looking at probably what we believe are sulfites, different kind of actually sulfur compounds that are maybe bubbling up from the surface into those cracks or being moved into those cracks. What does the surface look like from closer image? There's those red spots there, which maybe are bubbling up from the surface underneath, are 10 kilometers in diameter. Go down to about 230 meters per pixel. Now you're seeing how this really broken surface, really fractured. You could just, you're doing planetary geology. You're doing comparative geology. What on Earth looks like this? Icy surfaces moving, the glaciers moving. Think of plate tectonics. That's the kind of things you're looking at. If you get smaller, 200 or 20 meters per pixel, 6 meters per pixel. The surface is sort of different, different parts of Europa, our best understanding from Galileo. But, this is what you're looking at. And, this is where we want to go. We want to be able to land now on this kind of a surface. And so this is going to be a much more complex, the guys who did Mars landing was pretty complex, obviously. It's a different kind of complexity. We'll leave it at that. It's going to stretch us in a different dimension. It's going to be fun. So why are you doing this? We're looking at it on the right here. And so you're looking at Europa. This portion up here, maybe depending on what's actually there, and we only have best guesses scientifically. This might be on, if you take a bunch of scientists and you said, give me the number, and they're going to say 10 kilometers. Some will say, oh, no, it's only 2. Some will say 100, but talking to the best, one of the key guys in Europa science, he thinks it's about 10 kilometers of ice, and then you have, this is liquid, this is water. This is H2O water, probably with all those salts that are coming up from the surface or being pushed down from the radiation environment on top, being bombarded with ions, most likely sulfide ions. And then because of all that movement you're looking at plate tectonics over there, you're looking at it move. So right now you want to get a better understanding of what this is based on the data we have. You can see the models that are started being developed to understand this. So one of the things I'm looking at with a team is I'm an electromagnetics background, leading to radar, signals through the surface, low frequency radar understanding. We hope to launch a system in 2022, the Europa Clipper, and with that we also hope to have a landed element to it, sort of a technology-driven lander to get to the surface to really smell and sniff. We will absolutely have to have a radar on that system because the radar can penetrate through this ice and get down through the ice into the water. What do we want to do? We just want to characterize how much ice is there, the actual thickness. You want to characterize it, over hopefully the whole moon. And it should be thicker or thinner in some parts. And then you want to look at if there's any shallower parts. If you want to look at where maybe the water is driving up through cracks, through these subduction zones or extraction zones up to the surface, and use a couple radar signals to do that. And then dig deeper into the science. Europa runs around Jupiter with a 3-day orbit. It's just flying around it. And so the tides, you have all this water just on Earth. The tide, the water is tidally driven. That tidally driving, keeps it from freezing and produces a lot of heat. The surface of it is, 100 100 degrees Kelvin on the surface, and then on the bottom it's got to be 32 degrees Celsius, 278. So you have this gradient of temperature. This is a fun place to go look at. And so we're putting together then what we think the surface is, and then it's going to lead to, first off, we want to have some really extensive models that look at radar signals from the orbit of Europa through the various ice levels that we could predict, simulate ahead of time to understand what we think we'll get later on. And once we get the data, we can start retrieving them. And so we have to look at, it's going to be a very complex surface, a lot of thoughts on what the surface may be looking like down at the, at the meter level scale that we can't see yet. Things that are related to that at Earth, up in the glaciers, up in the high altitudes where the ice is different than when it's down low. And then, the rough surface, ice going down through water, a lot of different scale sizes that have to be looking at. So my background, so I want to just put this all on a big computer and start modeling it. Model that rough surface, model the ice, different thicknesses, model down to the water, look at the return so that I could get a sense of a radar tone, put a pulse out, what comes back when to give me all this information. Well, when you start looking at the problem for Europa, for a radar, and that's the size of the beam that would be sitting there, we're looking at problems that are blue waters, at least class a problem, if we had the algorithms to handle it. That's where we're at with it. And so we're looking at possible full wave solutions, but then we're going to put up a whole class of algorithms that probably get us there. And at the end of the day, you'd like to have a set of predictive codes, which are not only going to do the science result, but then tell you how to design the radar system. And in the radar system, you could have wide pulses, narrow pulses, long pulses, short pulses, different frequencies, and so forth. So you have a lot to play with in an optimization. So we're getting down to the point where then it's, how to do this. And so we're starting to look at different pieces of the model, free space propagation from the Europa Clipper and the radar on top down to the surface. And then you have this, funky surface, that has to be understood, a rough surface, stochastic in a certain way. And then there's going to be all sorts of point scatters, and that field will not be coherent. And so you'd like to put together a large simulation that has all these kind of characteristics so that we get a better understanding when we go there what we're actually going to see, and again, how to design that radar ahead of time. So another class of problems. So what I showed you basically are three classes of problems. The engineered problem up front and where we want to go with that. Then data science is just going to become more and more key, obviously. And then this kind of scientific and instrument development where large computing, physics-based modeling, large data all have to come together. It's got to play in there. It's always been hard in NASA to try to drag NASA along into this world because there's just a lot of components. You have all the engineers, you have the scientists, you have limited resources and so on. So we try to keep dragging along to make these things happen, and we hope we will more and more. So the last couple pictures here. Here's one of my favorites. Again, the landing spot on Mars. When we landed on the planet, and it came from space. It landed. There's the two again spots where the propulsive engines kicked up the dust, built, actually dug up a little bit, and then the first tracks. So that is the the fun spot of where we landed. One day, maybe an astronaut will go back there and take a look at that. And yep, that's where Curiosity landed on April 6th. And then my last slide here, if you think about why you do this in the greatest picture, greatest viewpoint, to the left here, and our lab director put this slide together. On the left there, Apollo, a footprint on the ground for Apollo on the moon. And then on the right, the rover went up a sand dune and kind of pushed over the edge a little bit and looked out over the edge and what it saw. And at the bottom line, I think this is what drives most people at the highest level on why you want to work on this. So with that, I'll call it quits. Thank you very much. Appreciate the time to be here.
We have both time and a microphone here for questions. Oh, microphone's coming your way.
Could you say something about the software strategy at JPL? Do you use open source software? Do you
Yeah.
develop it in-house? Do you worry about sustainability and so on?
It's, well, a strategy would be maybe too big of a way to describe it. There are a number of strategies depending on the area. Chris Mattman there is a real force and vocal advocate. Open source strategy, Hadoop, for the large data. He's involved in the big data science. And so it's some combination of he's actually really driven within NASA an open source community. So taking what exists in the open source community and as well as pushing or funding areas out in the community that are doing this for the NASA needs, and then the things we do internally, turning that into back to the open source community. In fact, he's made a big change in that it's now not hard to put your stuff back into the open source. So that's on the data analytics, big data side. More on the engineering side, it doesn't have that kind of, I wouldn't say there's not that kind of strategy. We're sort of bringing in suites of codes, moving from specific engineering codes to more suites. We worked with Sandia for a while, and trying to get that integrated in for engineering design. And so those are, I think, the two biggest pieces of how we make that happen.
Is it like you get the raw data, or is there any pre-processing on board just to lower the volume, or what's the
raw? How does the data come in, or what type of data is it?
Yes.
Yeah, it starts with raw data. I mean, it's literally bits of some of it's maybe a data in the thought of a data cube, for example, X, Y, and then frequency of so many bits of per pixel. So it's very raw data. We call it level 0 data, low-level data. And then that actually goes into the archive. And then there's various levels of analysis put on top of that data that brings it to higher level of data where at the end it's information. At some point, scientific information at the end. So today it's, in today's world, in yesterday's world maybe, as it moves forward, the raw data was archived. And then there's a policy on the archiving and the release of the raw data based on science and so on. And then there's a release of various forms of that data. If it's level 0, it's got to get cleaned up to level 1, where you take away some of the instrument noise and so forth that only the team can do. And then at that point, it gets released in various manner over a certain amount of time. You like to speed up that process, make it quicker to come out to the community and so on. That's a piece of what's needed in the future. I don't know if that answered your question.
No, I meant on board, like the.
Oh, on board.
Is
yeah,
there,
okay,
because
great.
that's how you lower the transfer volume.
Yes.
Like
yes.
what's
So
the
on board,
pre-processing?
Simple things like compression, on board, some part of the community only has to have, it's got to be perfectly lossless compression, that you're not losing anything. We have projects, we have onboard software, even on the rover, because we keep uploading the software. The nice thing about this is that software is uploadable. We can just put up whole new algorithms to these systems on orbit and so forth, where you have decision making on board, where you can actually grab the data, the frames, and maybe have the previous orbit in there and look at differences. And if you saw a difference, then you can actually retrain your instruments back on what changed in a certain definition of change on orbit. And so that's going to be driven a lot by the flight computer. And so we need this new flight computer to give us the oomph, the flops, basically, to drive this. So on board, I think is really got a law. It can advance very quickly for onboard processing. The part of the struggle always is, I mean, these are science missions. They are science-driven missions, and all that data wants to come back to Earth. You know, it's wanted that all that data comes back to Earth, every raw bit, so you're not going to throw it out. Though, you know, there's going to be a conflict for that in the future because there's going to be so much data up there that's taken. So we're moving into this realm, I think, where when you get more data on board, it's going to be that question of how much you're doing on board. And we need some technology to push that with the computing, disks and so forth. I think that could come along. And then there's going to be a question of how you do it. And that's today an open question.
In your estimation, how far away, how long away are we from settling a Goldilocks planet? And are there some good candidates?
Exoplanets? Mm-hmm. Yeah, that's such an accelerating field. You know, I mean, we thought it was going to take decades, and now we have, there's another great display in my building where we have 9 habitable planets that we found from Kepler. And, you know, another several hundred, which we take to be candidates, which I'm sure will be, many of those will be in the Goldilocks zone for exoplanet, and many thousands we haven't even looked at yet in Kepler data. So the question, so if your question is, when are we going to find a habitable planet that has Earth-like signatures? Man, if I could answer that one, it would be special. But let me frame the question like, we have, there's another mission coming up, TESS, which is going to do a big survey in a few years. So but it's more of a survey mission. So we're going to have, in 5 years' time, a really lot of candidates for the habitable, hundreds and hundreds, thousands probably. And then the next mission we're going to fly then is one that's going to be able to zoom in on some of them. Okay, and so I would claim probably hopefully in 10 years' time that the mission after the next one, 2018 or so, we will have a mission up there which will have a coronagraph, have some instrumentation or a big star shade, something which is going to be able to really zoom in on some of those, look at 100 of them, and probably find 2 or 3 which are going to be the real deal. And so I would think that in reality, realistically, in 10 years, we'll be able to do that. It's going to be about 10 years out.
Do you expect to find life?
Yeah, well, yes.
In the simulation, all the time simulation depends on or needs simplifications and assumptions so you can reduce the cost. How can we close the gap between the assumptions and simplifications and the reality, especially if we will be landing and we'll face a lot of odds on the reality. Right. So how can you close this gap? So you can guide the landing on using close to the real life situation.
Yeah, it's going to be this mixture of giving enough smarts to the landing system. For example, if you're in a landed system, you're going to have to have some onboard computing and some imaging that feeds back to your rocket engines so that in a few minutes' time that you have, you're going to go land safely. And so there's going to be a mixture of picking spots to land which are interesting enough but are not going to kill you for sure. And then having enough smarts on board which allow you to drive to a safe landing area and have enough confidence that that system that you built operates like you expect. If you remember the Philae lander on the Rosetta mission that the Europeans did, phenomenal mission, revolutionized comet science today. There's the orbiter or trailing mission and then a lander, and it landed but it bounced. A couple things didn't work on it. It was supposed to put a harpoon in the ground and grab itself, and actually have a thruster to push it back down all at once. And it just didn't work because part of the deal. And so it's creating this sweet spot where you have enough complexity in your to handle the unknowns, but picking the right spot, and then but it's going to have to be driven by, to get to the interesting areas, by having the autonomy on board do more of it, do more.
Tom, here's a question. So you said you guys are doing tons of simulation before you actually send something to these far objects. So how you actually verify those numerical results? Because, there are no experiments there, right? If we are down to Earth, we are designing the car, so we can crash the car, we can verify our finite element model. So what do you guys do, do the equations actually apply still, the equations from the Earth?
Yeah, so you test a lot. You're testing a lot against the model. So there's a model for, I don't know, pick one of your favorite things, So we test a lot, for landed system with terrain relative navigation, something we're trying to really finish up for the 2020 mission. You're grabbing an image, and then you're characterizing that image on board, and then you're saying that image has rocks of a certain size, and I'm going to avoid them. So we go out to the desert. So we build a similar system. We model that system, and then we take it out to the desert. We drop it off of helicopters, and we test the heck out of it as much as we can, and model and validate against the models. Validate the models to what you got. So then we go up to places where we don't know what it is. You have some confidence. So it's really testing, and we're trying to get to the point where you're testing the right things against the model, so that the model's getting validated at the appropriate level. You don't build the whole thing and then try to test it, right? You do this incremental approach where you're putting little pieces together, model the little pieces, and put the bigger ones together, and keep going like that. It's, that's where we want to be in the future.
One more question.
Very nice talk, Tom. I was wondering if you could tell us a little bit more about the planetary data archive system and how it differs structurally from ESDIS, the Earth Data Archive System, and whether NASA has plans to merge the two in the future.
Yeah, the Earth, the NASA data systems, I'm an outsider looking at them, are very disparate. There's a lot of different ones in different places, and Earth is different than planet. The Earth is different than the other planets. Okay, Earth is a planet, as my Earth science friends like to say. So if you're going to combine them, right? They should be combined, and you want to combine them by engineering, computer science, data science-based reasons. You want to go back and look at the data or bring new data in, have metadata that's common among them, put them in archives, which is common, which could be commonly acquired. And so, you're moving from this legacy system, and I bounce, I sit around talking with my colleagues in this field. And should you just shut down the old system and start from scratch, right? There's a huge, big cultural change in doing that. Can you evolve it somehow? And so they should come together. And I believe what's needed is some, NCSA class people saying, giving answers to, given some possibilities, some real life possibilities on how to do that in the future, given what you have today, So it's a tough problem. It's a tough problem.
Okay, we're going to wrap it up for today. Tom, as a non-scientist, you sure had us fooled today. Please join us out here in the lobby for a little bit of a reception afterwards. Tom will have some time to join us there as well. Please thank Tom for being here today.